Hello. In today's video we're going to talk about ionic solids, looking at the properties of ionic solids and looking at the unit cells themselves. So an ionic solid is where we have an anion unit cell with cations filling the interstitial holes. So I'm going to do anion-based unit cells. So the unit cell is based on the structure of the anion. So at the corners we have anions. And then the stuff left behind, the empty space with no atoms, that's where our cations fill in. Okay, so in this structure, each anion is surrounded by cations, and each cation is surrounded by anions. So we have a charge balance going on, and we don't have any repulsion, so we have just attractive forces here, ideally. Okay, so it is this structure that causes us to get the properties of our ionic compounds. So here are properties. First we have a brittle substance. It's hard and it's high melting. Okay, so remember that we have a structure where we have ions beyond count. So we have a bunch of cations and anions. And we have attractive and repulsive forces going on. Or we're trying to maximize attractive forces and minimize repulsive forces. So let's look at this picture right here. So let's take 2 dimensions of our 3-dimensional structure. Let's say we apply an external force. So in this case, a hammer. So like what we do with a metal. But why does it not behave like metal? So we apply external force, and what happens is we shift. So we get a shifting of our cations and anions, and instead of having attraction going on between all our cations, or cations surrounded by anions surrounded by cations, we form repulsions. Those repulsions cause a crack in the crystal. So that's why we have such brittle substances. They're also very hard because prior to what we did where we cracked our ionic cell, or our ionic crystal, we have positive and negatives all over the place that are really, really attracted to one another, holding the whole structure in place, making it very high melting. Also remember, when we're melting, we get a breaking of ionic bonds. So another reason why we have such high melting points with these. Okay, so with our ionic structures, we want to maximize our attractive forces while minimizing our repulsive forces. So our ionic substance, we want to maximize attractive forces, and we minimize repulsive forces. So our attractive forces, positive and negative together, repulsive, positive, positive, or negative, negative. So we want to try and minimize positive and positive together, negative and negative together, but we want to get as much positive and negative close to each other as possible. So we do this by kind of maximizing the amount of anions you can get around a cation without touching our anions together. So we maximize cation coordination number. Remember, that's Cn plus. While not having anions touch. Okay. So we want to minimize repulsion. So we look, in order to do this, we look at the radii of the cation and anion. Okay, so what we want is as many anions around our cation as possible without them touching. So in this arrangement right here, we see this. Here we have a maximum number of anions around our cation, but our cations themselves are not touching. There's space in between them. So that is what we want to do. So we're going to look at what's called a radius ratio. And this is how we can get maximum stability. So we're going to look at the ratio between the cation radius, and I'm going to call this radius ratio, we're going to call it RR. So our radius ratio is equal to the radius of our cation and we divide it by the radius of our anion. And we're going to get some number. And that number is going to relate to what type of basically cation hole we can put our cation in. We're going to have radius ratios between 0.732 and 1. So this is where they're close to the same size. Or between 0.414 and 0.732. This is a medium, or I'm actually going to say relatively medium to large cation. And by relatively, I mean relative to the anion. And then lastly, 0.225 to 0.414. That's going to be a relatively small cation. Okay, so those are the ratios we're looking at. Let's look at each of these kind of scenarios to see where we get this. So the first one we're going to look at is when we have a cation which is similar in size to the anion. So this would be a large cation relatively. So here is what that looks like. So the 0.732 to 1 radius ratio gives us a cubic hole. We call that a cubic hole for cation. And this is where we're going to maximize our cation coordination number. So as we can see here, our cubic hole, which is this right here, is when we have a cation in the middle of a primitive cubic arrangement of anions. It looks very much like a body-centered unit cell, but a body-centered unit cell, the center is the same as the corners. In a cubic hole, we have a cation in the center of a primitive cubic arrangement of anions, so slight differences. Here, with our cubic hole, we have a coordination number equal to 8. So that center cation is surrounded by 8 anions. Okay. And this arrangement that we have here, like I said, that it looks like a body piece, but it is not. So not a body piece. But it's basically the greatest cation coordination number we can get, and it's when we have a very large relatively large cation. Next we're going to look at is called octahedral. So an octahedral cation hole. Here, the cation basically takes on a octahedral-like geometry, where we have our cation surrounded by 6 anions, and it forms like an octahedron shape, like we saw in molecular geometry, right? So here's what that looks like. We have our octahedral cation surrounded by 8 anions. So we have a coordination number for our cation equal to 6. I think I might have said 8. I didn't mean to. So we have 1, 2, 3, 4, 5, 6 anions surrounding our cation, and it makes an octahedron shape, which is why we call it octahedral. So this occurs specifically in face-centered cubic arrangements of anions. So our anions are forming a face-centered cubic, and if you're not sure which one your anions are, they're going to be the ones that are on the corner. So here we see on the corner, that's our chlorine, and it is a face-centered arrangement. With our face-centered arrangement, we have octahedral cation holes. Okay. So all these purple balls, that's our cation. Green balls are our anions. Yeah, there's one thing I didn't note up here. Here, there's only one cubic hole per simple cubic unit cell. Okay, so the maximum we can have here is 1, just as a note. Okay. Here, the maximum that we can have in a face-centered, the maximum number of octahedral atoms will be a total of 4. So there are 4 total octahedral holes in a face-centered anion geometry. Okay, so we can see, hopefully, the center one right here, that accounts for 1 atom, and then each of our edge pieces, which are what these are, and edge pieces are only seen for our cation holes, which is why we didn't talk about them initially, but our cations can occupy edge pieces, and each edge piece is 1/4 of an atom. And there are a total of 12 of those. So if we have 12 edge pieces, that's 3 atoms, and then the one in the center would be our 4th, giving us 4 total octahedral holes actually within the unit cell. So we have a maximum of 4. Not all of them have to be filled. as a note. So sometimes you'll see that half of the octahedral holes are filled or something like that. If half the octahedral holes are filled, we only have 4 atoms within the unit cell. Okay. Now, we get octahedral cation holes for medium to large cations. So again, relatively. If we have small cations, that we're going to form tetrahedral, or we'll put them in tetrahedral holes. Okay. So here it looks like a tetrahedron. So we've got our cation surrounded by four anions. So we have a positive coordination number equal to 4. This is what it looks like in a much prettier way. So we have our 4 atoms, or 4 anions specifically, surrounding our cation, making a tetrahedron shape around that cation, which is why it's called tetrahedral. So this also occurs in face-centered cubic, or it occurs in a arrangement of face-centered cubic anions. So in face-centered cubic arrangement of anions. Okay. This is a much smaller thing, a much smaller hole, so we can actually get a larger amount. So if we were to take our face-centered cubic and break it into 8 quadrants, we can have a tetrahedral hole in each one of those quadrants. So there are a total of 8 tetrahedral holes. So we can hold a total of 8 cations if they're all filled, but of course not all of them will all be filled. This is an example, copper chloride, where we have only half of our tetrahedral holes filled. So 1, 2, 3, 4. 4 of those are filled. The other 4 are unfilled, so just depends on your ratio of cation to anion number, your empirical formula. So your radius ratio will tell you what type of cation hole you will put your cations in, and then your empirical formula will tell you how many of those cation holes are filled with cations. Okay. So just to kind of summarize what I was just talking about, here on the left we see our radius ratios. We have our coordination numbers for our different radius ratios and the cation hole type. Okay, we do not get a radius ratio of exactly 1 for anything but metals, so just as a note. But we can get 4, 6, and 8 coordination numbers based on what type of cation hole we have. Okay, so let's look at how size affects our structure, or ion size affecting our structure. Okay, so as we decrease our cation size, so going from a cubic to an octahedral to a tetrahedral, we're going to decrease our radius ratio, right? And we're going to decrease our coordination number. Okay, so here are 3 examples. We've got cesium chloride, sodium chloride, and zinc sulfide. In here we are decreasing our cation radius, and as such we're decreasing our radius ratio. Here are anions basically the same in size, and we get a cation coordination number that also decreases. because we have a 1-to-1 cation to anion ratio in this particular table, we have a equal cation coordination number to our anion coordination number. And we can determine our anion coordination number as well. So we can figure out our anion coordination number using our cation coordination number and our number of atoms in our unit cell. So we take our number of cations in unit cell divided by number of anions in unit cell. And this ratio will be equal to the coordination number for our anion over the coordination number for our cation. Actually, just going to do Cn minus over Cn plus. Okay, so those ratios will be equal to each other. And here we go, looking at our anion to cation ratio. So coordination number of 6. They are equal to each other, so we'll have a anion coordination number of 6. If we have a 1-to-2, the cation coordination number is 6. Our anion coordination number will be half of that. 1-to-3, 6-to-2 for our anion. Okay. And that completes this video. See you guys later.